Alright, hey guys, this is Mr. Thomas. Alright, so this is Chapter 7, Covalent Bonding. So, Lesson 1, the covalent bond. Here's your essential questions for this lesson. So, how does the periodic table help you determine the names and formulas of ions and compounds? And what is the difference between an ionic and molecular compound? Alright, so here's your topics and sections for this chapter and this lesson. So, why do atoms bond? What is a covalent bond? We'll talk about single covalent bonds, multiple covalent bonds, and we'll also talk about the strength of covalent bonds. All right, so here's your vocab. So covalent bond, so that's going to be a chemical bond that results from the sharing of valence electrons. Molecule, that's going to be when two or more atoms covalently bond. Sigma bond, that's going to be a single covalent bond that is formed when an electron pair is shared. Pi bond, that's going to be when parallel orbitals overlap. Lewis structure, that's just going to be the electron dot structure. And endothermic reaction, that's going to be when energy is going into a reaction. Exothermic is when energy is being released from a reaction. So, why do atoms bond? So, atoms are going to bond because they're going to gain stability. So, when they bond, they're going to gain stability. So, the way they're going to gain stability is, remember the octet rule? So, each one of the atoms wants to get a complete 8 valence electrons for it to be stable. Previously, we were talking about ionic bonds. So, ionic bonds are going to transfer electrons. So in the case of, let's say, for example, sodium chloride. So for sodium chloride, we had NaCl. Sodium had 1 valence electron. So I'm going to put that 1 right there. Chlorine's going to have 7. So sodium's going to transfer that 1 electron to chlorine. So now we have sodium, that's going to be a positive charge. We're going to have chlorine, that's going to be a negative charge. Positive, negative, opposites attract. Then we have NaCl. So that's an ionic bond. All right, so going back to here, covalent bonds, they're going to be shared. Covalent bonds can be sharing electrons. So now we have shared electrons. So when atoms are going to be sharing their electrons, that's going to be a covalent bond. So a molecule is going to be when two or more atoms bond covalently. So now we have ionic compounds and covalent compounds. So ionic compounds, which we talked about last chapter, those are going to be between atoms that are transferring electrons. In this chapter, we're going to be talking about covalent compounds, and they're going to be sharing valence electrons. So that's going to be through covalent bonding. All right, so in a covalent bond, we're going to have shared electrons, and it's going to be between their outer energy levels. So if you remember our different orbital types, we're going to have S, P, D, and F. So our outermost energy levels, our outermost orbital types, that's going to be S and P. So those are going to be the orbitals that are going to be sharing valence electrons. All right, so covalent bonds, they're going to be generally near each other, and they're also going to be between nonmetals and nonmetals. So if you remember back with ionic compounds, those are going to be with nonmetals and metals. Covalent bonds are going to be with nonmetals bonding with nonmetals. So now I want to talk about specific type of covalent bond. So we have diatomic molecules. So for diatomic molecules, if we look at this, so di, that means 2 atomic atoms, and then molecules, that's going to be covalently bonded, right? So 2 atoms that are going to share electrons. So these are a special type of covalent bond. So they're going to be, for example, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So if you look at these, so each one of these has 2, so diatomic, 2 of the same atoms bonded covalently together. So there's two atoms, and they're going to be sharing their valence electrons. So here I'll show you on this. So we have hydrogen, so that's going to have one valence electron. We have another hydrogen, that's going to have one valence electron. So when they come together, they're going to be sharing these two valence electrons. Now, you guys know what a Venn diagram is. So if you have this hydrogen, and you also have this hydrogen, since they're going to be sharing these valence electrons, each one of these hydrogens both have two electrons. All right. All right, what about, for example, oxygen? So we have oxygen and oxygen. So oxygen's going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. All right, so they're going to be sharing these two valence electrons. So it'll look like this. All right, so now each one of these oxygens is going to have 8 valence electrons. So this oxygen on the left has 2, 4, 6, 8 valence electrons, and this oxygen on the right is going to have 2, 4, 6, 8 valence electrons. Remember, for our octet rule, we're going to need to have 8 valence electrons for it to be stable. So since they're sharing these electrons, they both have 8 valence electrons. So for diatomic molecules, we're going to have 2 of the same atoms, and they're going to both have their noble gas configuration. And they're going to be more stable together than by themselves. So let's take an example. Let's consider fluorine, which has an electron configuration of 1s2, 2s2, 2p5. So for valence electrons, we're going to have 5 plus 2, since this is our outer layer. So that's going to be 7 valence electrons, which means it's going to need one more electron to form an octet. All right, so as two fluorine atoms are going to come together, we're going to have two repulsive forces and a force of attraction. So let's just draw this out. So we have fluorine, right? So two fluorines. How many valence electrons does each one of these have? So we're going to have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the forces of repulsion, those are going to be the protons in the nucleus of this fluorine, and the protons of this fluorine are going to be repulsing each other. Remember, opposites attract, same is going to repulse. Same thing with the electrons, so they have the same charge, so they're going to be repulsing one another. However, for our force of attraction, the protons of the nucleus in this fluorine are going to be attracted to the electrons over here, and the protons in the nucleus are going to be attracted to the electrons over here. So there's a balance between them. All right. So two repulsive forces, so that's going to be from the electrons, and the protons against the protons, and the force of attraction, that's going to be attracting the protons and the electrons. All right, so remember that fluorine is going to be a diatomic molecule, so it's going to need two identical atoms of fluorine, and when they come together, each one of the fluorine is going to share one of its valence electrons to achieve a noble gas configuration. So let's go back to here, so let's draw it out. So we have these two fluorine atoms, so this fluorine atom is going to come over here, and now they're going to share their valence electrons. So if we have that, so how many does the fluorine on the left have? So we have 8 valence electrons, and on the right, we're sharing our valence electrons, and we're going to have 8 on the right. So that's all that this is showing. So we have our 8 valence electrons, so we have 3 of these lone pairs, and then we're going to have our sharing electrons. and this fluorine on the right, that's going to have 3 lone pairs, and we have sharing these 2 valence electrons in between them. So this slide is just showing you the same thing. So each fluorine atom in the fluorine molecule is going to have 1 pair that's covalently bonded. So these ones in red, they're covalently bonded. And we're also going to have 3 unbonded pairs. So 1, 2, 3 lone pairs on the right, and 1, 2, 3 lone pairs on the left. So these unbonded pairs are also called lone pairs. All right, so when only 1 pair of electrons is shared, it's called a single covalent bond. So if we go here, so for example, we have hydrogen, so H, H, this one has 1 valence electron, this one has 1. So when they come together, so when these 2 come together, they're going to form a bond, and that's only 1 bond. So there's 2 different ways that you can write this out. So you can write this just as this, or you can also write H2 like that. So this line is the same thing as these 2 dots. It's just another way of writing it. So this means that there's a covalent bond between these 2 hydrogen atoms. So for example, we have a hydrogen molecule, which I just drew out. So they're going to be sharing their pair of electrons, and this is called the bonding pair. So here again, I show you there's 2 ways of writing it. You can have H dash H or H and 2 dots H. All right, so group 17 and single bonds. So this is going to be the halogens. So if you look at your periodic table, your halogens are going to be group 17, all the way on the right-hand side of the periodic table. So that's going to have some like fluorine. So they're going to have 7 valence electrons. So for here, we have fluorine 2. There also is chlorine 2. So if we draw those out, so we'll have fluorine. So fluorine, fluorine. Each fluorine is going to have 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So each one has 7. So if we bring them together, they'll both have their octet. All right, so same thing with, let's say, chlorine. So chlorine is going to have 7. Chlorine, chlorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So if we bring these 2 together, they'll also have their octets. Right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Same with chlorine. 2, 4, 6, 8. 2, 4, 6, 8. All right, so group 16, if you look on your periodic table, so group 16 is also on your right, so that's going to have oxygen, sulfur, selenium, tellurium, so those kinds of elements. So if we have, for example, let's say oxygen. So we have oxygen, it's going to have 1, 2, 3, 4, 5, 6 valence electrons. So we're going to need 2 electrons to fill in its 8. So 1 atom that has a single electron is going to be hydrogen. So we're going to have hydrogen, and we'll have a hydrogen here. So hydrogen is going to have 1 valence. That's going to have 1 valence. So if we move these 2 hydrogens over, so move that one there, and we also move this hydrogen up here. So now hydrogen is going to have its 2 valence electrons that it needs. Hydrogen's going to have its 2 valence electrons that it needs. And then oxygen is going to have its 2, 4, 6, 8 electrons that it needs. So that's all this is showing here. So for group 16, they're going to share 2 electrons. So here we have 1s2, 2s2, 2p4. Our outermost valence electrons are going to be 2 and 4, so that's going to be 6. So 6 to 8, we're going to need 2 valence. So here we also have hydrogen, hydrogen. And remember, these dashes, that's going to mean a covalent bond. So these means 2 dots here. It's just another way of writing it. So group 15, so if you look on your periodic table, group 15, that's going to have nitrogen, phosphorus, arsenic. So those are going to have 5 valence electrons. So one example we have here is going to be ammonia. So we have nitrogen, and that's going to be with 3 hydrogens. All right, so let's go to our blackboard. So we have nitrogen. So nitrogen, so how many valence electrons does nitrogen have? That's going to be 1, 2, 3, 4, 5. And then for hydrogen, we're going to have 1. Hydrogen's going to have 1. Hydrogen's going to have 1. All right, so for each of these, when they covalently bond, this is going to move over here. And we're going to have this hydrogen. It's going to move over. And then this hydrogen also going to move over. So how many valence electrons does this hydrogen have? So it has its 2 that it needs. Hydrogen, that's also going to have its 2 that it needs. And this hydrogen is going to have its 2 that it needs. All right, so for nitrogen, how many valence electrons does nitrogen have now that it's sharing? So we have 1, 2, 3, 4, 5, 6, 7, 8. So our octet rule is fulfilled. All right, so that's all that this PowerPoint is showing. So group 15 is going to have single bonds with 3 nonmetals. So electron configuration, that's going to be 1s2, 2s2, 2p3. So our outermost energy levels, so that's going to be our 2s. So we're going to have our s and our p's. So 2 plus 3, that's 5 valence electrons. All right, so ammonia is going to have 3 hydrogens with 1 nitrogen. So that's what we have here. So 1 nitrogen is going to have 1, 2, 3, 4, 5 valence electrons. Hydrogen is going to have its 1. Hydrogen is going to have 1. Hydrogen is going to have 1. So 5 plus 3 valence electrons is going to equal your 8 for your octet. So for group 14, we're going to be in group 14 on a periodic table. So if you look at group 14, we have carbon, silicon, germanium, and tin. All right, so here we have carbon with 4 hydrogens. So here we have carbon, we have 4 hydrogens. So carbon's going to have 4 valence electrons, hydrogen's going to have its 1. So we have carbon with 1, 2, 3, 4 valence. Then we're going to have hydrogen with 1 valence, hydrogen with 1, 1, 1. So 4 from the carbon, and then 1 from each of these hydrogens. That's going to equal our 8 valence electrons. All right, so let's just draw that out. So we have carbon in the center, so C has 1, 2, 3, 4. All right, so for hydrogen, that's going to have 1, hydrogen, 1, hydrogen, 1, hydrogen, 1. So how many valence electrons does each one of these hydrogens have now? So now each hydrogen is going to have its 2 that it needs. Carbon is going to have its 8 that it needs. So 1, 2, 3, 4, 5, 6, 7, 8. So now we're perfect. All right. So go back to here. So group 14 is going to form 4 covalent bonds. So methane is going to be CH4. Carbon's going to have 1s2, 2s2, 2p2. Our valence electrons are going to be the outermost s and p orbitals. So it's going to be 2 plus 2, so 4 valence. That's what we have here. 1, 2, 3, 4. So it's going to form 4 bonds. All right, so now I want to talk about sigma bonds. So sigma bonds are going to be what happens when these orbitals are going to overlap. So here we have s orbitals overlapping. Here we have p orbitals overlapping, d orbitals overlapping. So they're coming head on to each other. So single covalent bonds are also called sigma bonds. So if you look back here, so each one of these single bonds, single bond, single bond, single bond, so these are all sigma bonds. All right, so this is going to be when atomic orbitals are going to overlap end to end. So here we have end to end, here we have end to end, end to end, end to end, end to end. All right, so let's just draw that out. So if we have, let's say, an s orbital and an s orbital, we're going to have 2 valence electrons in between them. So these are head-on, they're overlapping. Or if we have a p orbital and an s orbital, we're going to have 2 valence electrons overlapping. Or if we have a p orbital and a p orbital, so these are going to also overlap head-on to each other. So here you can see we have sigma bonds. So here's an s orbital and a p orbital. They're overlapping. Here's an s orbital from the hydrogen and a p orbital from the carbon. They're overlapping. Here we have overlapping. Here we have overlapping. So these are all sigma bonds since they're all overlapping head-on. All right, so sigma bonds can form between s orbitals overlapping s orbitals overlapping p orbitals, or 2p orbitals overlapping. So same thing that we have over here. So we have s orbital overlapping s orbital. Here we have s orbital overlapping a p orbital. Here we also have a p orbital overlapping another p orbital. So here we have water, here we have ammonia and methane. So multiple covalent bonds, so these are talking about covalent bonds that can have more than one bond between 2 atoms. So for example, carbon can have double, triple bonds, nitrogen can have a triple bond, oxygen can have a double bond. So how do you know if they'll form? It's generally so that it gets to the 8 for the octet rule. So for double bonds, for example, we have oxygen. So for oxygen, let's draw this out. So we have oxygen here. It's gonna have oxygen, oxygen. All right, so for oxygen, it's gonna have 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4, 5, 6 valence electrons. So for each of these to get to its 8, it's gonna have oxygen, oxygen. 1, 2, 3, 4, 2, 4. And it's gonna have a double bond here. So remember, each one of these dashes is going to be 2 electrons. Each one of these dashes is 2 electrons. So if we add these together, so we have 1, 2, 3, 4, 5, 6, 7, 8. Here we have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Another way we could have drawn this was oxygen, oxygen, 4, 2, 3, 4, 1, 2, 3, 4. So this is another way that you could have drawn it. So here we have it in dashes, here we have it in dots. So, oops. All right, so for here, on the left-hand side, we have our 8, and here, on our right-hand side, we also have our 8. Remember, these are shared electrons, so they belong to both atoms. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is what this is showing. So a double bond is going to be double covalent bond with two pairs of electrons that are shared between the atoms. So back over here, we have two pairs of electrons shared between them. So for example, we have oxygen. That's going to be a diatomic molecule. So it's going to have its 1, 2, 3, 4, 5, 6, 7, 8. This action is going to have 1, 2, 3, 4, 5, 6, 7, 8. So for a triple bond, we're going to have three covalent bonds, and it's going to be between three pairs of electrons. So for example, we have nitrogen here, so N2. So we have nitrogen, nitrogen. Each nitrogen is going to have 1, 2, 3, 4, 5 valence. 1, 2, 3, 4, 5 valence. So these three electrons are going to be shared. So we have nitrogen, nitrogen, 1, 2, 3, and then we're going to have a lone pair on the sides. So if we add up all of these shared electrons, we'll have, so 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen. And then on this side we have 1, 2, 3, 4, 5, 6, 7, 8. If you want to rewrite it with the dots, you can have nitrogen, nitrogen, 1. All right, so each one of these nitrogens is going to have 8 valence electrons, and then 8 valence electrons over here. So 2, 4, 6, 8. 2, 4, 6, 8. So nitrogen is going to have a triple covalent bond. Each nitrogen is going to share 3 electron pairs. So now I want to talk about pi bonds. So if you remember sigma bonds, so sigma bonds are going to be single bonds. You're going to find them when you have single bonds. Pi bonds, you're going to find them when you have double or triple bonds. All right. So when we talk about a single bond, so that's going to have one sigma bond. For a double bond, that's going to have one sigma and one pi bond. And then a triple bond will have one sigma and two pi bonds. So you're always going to have a sigma bond with doubles and triples. It's just a matter of how many pi bonds you have. So a single bond is going to have one sigma, a double bond is going to have one sigma and one pi. A triple bond is going to have one sigma bond and two pi bonds. All right, so for pi bonds, those are going to be for multiple covalent bonds. So for example, we have double bonds and triple bonds. So they're always going to have one sigma bond. It just depends on how many pi bonds. So if it has one sigma and one pi bond, that's going to be a double bond. If it has one sigma bond and two pi bonds, that's a triple bond. All right, so for pi bonds, that comes from the Greek letter pi, and they form when parallel orbitals are going to overlap and share electrons. So they're going to be parallel and they're going to overlap. So just to review, so remember sigma bonds, that's going to be a head-on overlap. So that's a sigma bond. If we have this, this is also a sigma bond. Or if we have this, that's also a sigma bond. So they're overlapping and they're head-on. For pi bonds, they're going to be parallel. So this would be a pi bond. So here's a picture of ethylene. So I'll just draw this out for you. So ethylene is going to be C, H, H. So this is ethylene, and we're going to have a double bond in between these two carbons. So there's a double bond in between these two carbons. These are going to be sigma bonds since they're single bonds. So if we have two carbons that are double bonded, how many sigma and how many pi bonds are going to be between them? So we're going to have one sigma bond and one pi bond in between these. All right. So here we would have our one sigma and one pi bond. So if you wanted to draw this out, so we have carbon here. We're going to have an orbital like that, an orbital like that. And then we can also draw in our hydrogens. And for our pi bonds, we're going to have orbital like this. All right, so what kind of bond is this? So it's head-on, so this is going to be a sigma. This one's going to be a sigma, sigma, sigma. Now remember, for our double bond, we're going to have a sigma and a pi bond. So for sigma, this one's going to be a sigma bond here. And then for our pi bond, it's going to be these parallel orbitals here. So these would be our pi bonds. So we have one sigma and one pi, and that makes up our double bond. So remember, for our double covalent bond, we're going to have one pi bond and one sigma bond. So here's our one sigma bond, and here's our pi bond up top and on the bottom. Now for a triple bond, that's going to have two pi bonds and one sigma bond. So for the strength of covalent bonds, some bonds are going to be more easily broken than others because covalent bonds differ in strength. So some factors that influence the covalent bond strength is going to be bond length and bond energy. So bond length is going to determine the strength of a particular covalent bond because the smaller the length between the two nuclei of two atoms, the stronger the bond. So here we have bond length, so we have fluorine, we have oxygen, we have nitrogen. So for fluorine, that only has a single bond, oxygen has a double bond, and nitrogen has a triple bond. So as you can see, so the more bonds it has between one another, the bond length is going to decrease. And the smaller the bond length, the closer they are, the stronger the bond. So as the number of pairs increases, the bond length decreases. And when the bond length decreases, the strength is going to be stronger between the bonds. So the shorter the bond length, the stronger the bond. So here you can see the shortest length here is going to have the strongest bond. So you can see here, fluorine is going to have a bond dissociation energy of 159 kilojoules per mole. Oxygen is going to have 498. Nitrogen's going to have 945. So the higher this number, the stronger the bond. So the shorter the length, the stronger the bond. So fluorine is going to be weaker than oxygen, and oxygen is going to be weaker than nitrogen. When a bond forms, energy is going to be released, and when you break a bond, you're going to have to add energy to break a bond. So the energy required to break a bond is called the bond dissociation energy. So to break these bonds, you're going to need more and more energy the more bonds you have. So this one has a triple bond, so you're going to need more energy to break them apart than you would a double bond. So bond energies, so the smaller the bond length, the greater the bond dissociation energy. In other words, the smaller the bond length, the stronger the bond. Here we have endothermic reaction, exothermic reaction, endothermic reaction, so it's going to be absorbing energy. Exothermic is going to be releasing energy. So for summary, we have covalent bonds going to be formed when atoms are going to share electrons. Sharing one pair, two pair, three pair of electrons form single, double, triple bonds. Orbitals that are going to overlap, they're called sigma bonds. Parallel orbitals are called pi bonds. Single covalent bond, sigma bond, but multiple covalent bonds are made of sigma bonds and pi bonds. Bond length is measured nucleus to nucleus, and bond dissociation energy is the energy needed to break a bond.